we've got both our original function g of x and the inverse of that function graphed together. Now you can see what's happened is our inverse is no longer a function. Okay? And the reason it's not a function is because it doesn't pass the vertical line test, right? I can take that line and I can move it across. You can see it crosses the blue, the inverse of g, in two places compared to the original function. Now, the reason that occurs has to do with when we take the square root. Okay, so when we take the square root of it, we have the positive and negative arms of our g inverse of x. That's what it creates. Okay, so it's possible that you started with a function, and when you take its inverse, it's no longer a function. So let's take a look at what this means. So domain and ranges of inverses. The domain of f at x becomes the range of the inverse of x, and conversely, the range of f at x becomes the domain of the inverse of x. And that makes sense. We're switching the x's and y's, so it makes sense that the domain and range between the two also switch. So if you state the restrictions on the variables as you algebraically manipulate the expressions, you will have determined the range and domain of both the original function and its inverse. Okay, so here is find f inverse of x and state the domain and range of both those functions. Okay, so let's start with this. Okay, the first thing I have to do is let y equal f at x. Okay, I have a restriction. X cannot equal -2. Okay, now I have to cross multiply in order to get x by itself. Now I'm not going to expand it at this point, okay, because what I want to do then is I want to divide both sides by the y, so I end up with x plus 2, which was in brackets, equals 1 over y, and now I've created another restriction. Y cannot equal 0. Okay, and this brackets here with the x is not doing anything, so I can actually subtract 2 from both sides. And now I can do my x inverse of y, and I end up with y equals 1 over x minus 2. And I also have that, in this case, x cannot equal 0. Okay, I let f inverse of x equal y, and I'm left with f inverse of x equals 1 over x minus 2. All right, so up to the point just before you did the switcheroos, all those restrictions relate to our original function of f at x. Okay, and anything after that has to do with the inverse. So this refers to the inverse. Now, I don't know if you recognize, okay, this has a parent function of the reciprocal function. So you're still creating a reciprocal function here. So this actually is a function the inverse is. So let's look at the domain and range. We're just going to set it up in this a little bit table here. So we have f at x and we have the inverse of x. When I look at f at x, its domain, if I go back, there's that restriction up there. So x is an element of real numbers such that x cannot equal -2. We also know that y is an element of real numbers such that y cannot equal 0. Now, if I look at the domain and range of the inverse of that, you can see that we did gain it right here. So again, x is an element of real numbers such that x cannot equal 0. And although in my algebra part, I didn't see something about the y, if we graphed it, we'd be able to see what the issue was, but it actually becomes cannot equal -2. Okay, so they actually switch around, and for this last one, if I graphed this, we could see that we would have an asymptote line at -2 for the y. So you can see that all it does is switch a row back and forth between those two. Okay, so remember a few different things. in the sense that sometimes when you do the inverse of function, you don't get a function back. It's something else. Unless you put a restriction originally on and you're only reflecting half of a parabola to start with, then obviously you would still have a function. Okay, so lots of mathematical pleasure tomorrow.